Dr. Charlotte Horsmans Poulsen she's a senior staff scientist at DuPont Industrial Biosciences, and she will tell us about enzymes as a tool to provide clean label solutions in food systems. Dr. Horsmans Poulsen, she has adjunct professor. She's adjunct professor at Aarhus University, and you're a board member of the Interdisciplinary Nanoscience Center, and also a member of the Danish Academy of Technical Sciences. And the floor is yours.
So first I would like to thank Jan and Per and the organizers for inviting me here to give this talk. I will talk about applying enzymes in clean label formulations. And first maybe just say that since this is about additives, that enzymes actually are not additives, they are actually processing aids, because they are active in the preparation of the food, but they are not active in the final food. They are inactivated during the processing. Talking about applying enzymes in clean label, I think a good starting point is to try and define what do we actually consider clean label. And that is actually a little bit difficult, because there is no clear definition of clean label. Consumers are skeptical and suspicious of ingredients they do not understand or recognize. That is clear. So for some consumers, a clean label actually means something where there are no ingredients that are hard to pronounce, or which are very unfamiliar to you, or that you do not know. That is clean label. For others, it is really some of these no lists that Lynn also showed, that you want to be sure these are not on the ingredient list. But there are certainly also people for whom clean label is a matter of it has to be organic, or it has to be not genetically modified, or it has to be socially, environmentally conscious. So clean label is not a clearly defined concept. Within DuPont, we think that what is important is that what is on the label is understood by the consumer, and we are transparent about how food is made. That is for us the key point. I have one slide showing some market survey that was done, looking into what is the top 5 level descriptors among clean label shoppers. And one of the things that come up across all the different groups is actually recognizable ingredients, as well as all natural ingredients. That is something that is being sought for everybody. If you are an older generation, it could also be things like low in sodium, as well as no sugar added is also asked for. And actually millennials are the only group where you have organic called out as an attribute that people would make them buy more. What I want to show you now is 3 examples of commercial solutions where enzymes are being used in creating, I call it here a simpler label, because the clean label definition is so undefined, but creating a simpler label. One is about using lipases to generate emulsifiers in situ in the bread, so you get the emulsifying effect in situ. The other one is a rather new enzyme we launched last year, which is a lactase, which is generating fiber in situ in, for instance, a yogurt, could be other dairy products as well, and where you then also will achieve a sugar reduction. And finally, I will show an example where we use an oxidative enzyme called hexose oxidase in bread, and show you how that compares to using bromate, which is being banned or is banned in a lot of countries. So first, lipases for emulsification in bread. What is the functionality we talk about here? Well, it's actually generating in situ the emulsifiers in bread, or in the dough actually, from the lipids that are naturally present in the flour. You have a synergistic dose strengthening effect created. The benefit of you having this emulsifying properties in dough is really that you improve the tolerance to processing variations and certainly also to raw material variations. I think it's very easy. If you bake a bread at home, you are perfectly happy if your bread is maybe flat or it's not totally the same from last time you baked it. It doesn't really matter. That's not why you make it. But if you are an industrial bakery and you are making thousands and thousands of bread per hour, you really need to have a dough that is very tolerant to, for instance, the stress. There might be a hold up in the production line and suddenly the dough, instead of racing for 1 hour, has to race for 2 or 3 hours. If you don't have a good strong dough, the dough will collapse and you can throw away your production. So this is much more a question of industrial production, of course. The lipases, because they are stabilizing the dough can retain the gas produced by the yeast better, and you therefore also will see an increased volume of the final product. And it improves the crumb texture for the same reason, and I'll show that in the next slide, or a few slides ahead. What is the substrate we talk about here? Well, if you have normal wheat grain, you have 2 to 3% lipids, naturally there. Half of that lipid will be non-polar lipids, the other half will be polar lipids. And again, the polar lipids you can split in half. Half will be glycolipids, half will be phospholipids. And you see the distribution up here. What is it then we are doing with a lipase? Well, in fact, we are talking 3 different activities. You can either, if we talk these non-polar lipids, that would be mainly triglycerides. And you can have a triglyceride hydrolyzing lipase, and it will cleave off one fatty acid and generate a diglyceride. This is all about creating something that is more polar. If it is more polar, it is better at stabilizing the gas-liquid interface and therefore stabilizing the gas cells in the dough. The same thing if we talk the phospholipids, here exemplified by phosphatidylcholine. You have a choline group, the glycerol backbone and 2 fatty acids. A phospholipase then cleaves off one of these fatty acids and we generate a free fatty acid and a lysophosphatidylcholine. The lyso component with 1 fatty acid is more polar, a better emulsifier. And then finally, the most potent group actually of all the wheat flour lipids is actually the digalactosyl diglyceride. It is a digalactosyl, glycerol backbone and 2 fatty acids. And the glycolipase will remove 1 fatty acid and you get a digalactosyl monoglyceride, a better emulsifier. You can also have a monogalactosyl diglyceride and create a monoglyceride. So these are what we are modifying. And what then happens is that because you have something being more polar, it is better at embedding itself, or it fits at the interface between the gas cell and the dough liquor. So what happens is you get a stabilization of the gas cell. And when the gas cells are stabilized, it means they are less prone to collapse with another gas cell, which would give you the inhomogeneous crumb structure where you get big holes. It also means that they are better at retaining the gas, which is produced by the yeast, and therefore when you bake the bread, the gas cells are expanding and you get the big volume. If you have an unstable system, the gas is escaping the dough and the bread collapses. And that's what can happen very easily when you do it at home in your kitchen, where you might not have a lipase to add, etc. And then another way of where you actually can see this effect is, for instance, if you measure the surface tension. In this case, we have actually taken the dough liquor, simply centrifuged the dough and taken the dough liquor and then measure the surface tension. And you can see how in the control, the pink, there is the surface tension is high. And then if you actually have a dough treated either with this glycolipase or with a well-known emulsifier datum, you will see how the surface tension is much lower. And that is the stabilization. How to apply this? This is showing one example from a product we are selling called Fiberline. The challenge when you make whole grain bread is that it is you very easily get a very dense and heavy bread, and in this case you can solve it to what is shown as solution 1, is a mix of enzymes and emulsifiers, and then you have to add 3% gluten to give you extra strength. In the middle we have actually made a solution which has only enzymes and then 5% gluten, and lipases is one of those solutions. And just for comparison, if you compare solution 2 and 3, in 3 we have only added the 5% gluten. So the only difference between 2 and 3 is the enzymes. And you really see how this makes a difference to the kind of bread you get out of it, both with volume, certainly also texture, and how your mouthfeel will be. And if we look at labels, this certainly gives a very clean label, or very simple label. You can see a labeling example, if you use this enzyme complex, is really fiber, flour, whole meal flour, water, gluten, vegetable fat, salt, sugar, yeast, and ascorbic acid. You can even do without the E number if you want, because we have a solution where you add acerola extract, so this extract from plants or fruit, which is very high in vitamin C or ascorbic acid, and in this way you would get a very simple label. So one example from the baking world, and then I would like to give you an example from the dairy world. This is a new enzyme we launched late last year, which is really in situ generating prebiotic fibers. So prebiotic meaning a fiber which is good for a probiotic like a bifidobacterium or a lactobacilli. And this is then also at the same time reducing the sugar in your dairy products. So just introducing the enzyme, it creates a dietary fiber that leads at the same time to a reduction of the lactose level. It reduces the lactose calorie contribution, and it brings down the total sugar content. How is this happening? Well, if you have lactose, it is a galactose and a glucose. It is very well known that if you add a lactase, it will cleave lactose. The way it does it is it will actually release glucose and it will bind galactose covalently in the active site. And then the enzyme can use water as the nucleophilic acceptor. And in that case, you have got a hydrolysis of your lactase into glucose and galactose. But you could also have that this galactose sitting in the active site use another galactose, a galacto-oligosaccharide or a lactose, as the acceptor. In that case, you will start building galacto-oligosaccharides. And galacto-oligosaccharides are very well known and have very good prebiotic claims, used widely in infant formula, for instance, because it's the best substitute we have for human milk oligosaccharides at the moment. Any lactase known today is able to produce galacto-oligosaccharides, but they will only do it if you have really high concentrations of lactose, because water is so much better acceptor. So you really need to go to hypersaturated or supersaturated lactose, meaning high, like 55% lactose and very high temperature. So this is not something you can do inside a food product. So today all galacto-oligosaccharide production, until we came with our new enzyme, is something done as a separate production of galacto-oligosaccharide, which you then have to add back into the product. Now what we then did was we used some publications and work done by Peter Staugård and his colleagues, where they actually had been working on a beta-galactosidase from Bifidobacterium bifidum. And what they discovered was, I should move over here. What they discovered was that this enzyme, this is the full-length enzyme. You have a glycoside hydrolase core, so this is where the catalytic reaction takes place. And then you have two galactose binding domains. The full-length enzyme is a normal hydrolyzing beta-galactosidase, not different from what is known. But what they discovered was that if you are truncating this enzyme and you actually remove the two galactose binding domains, you suddenly will see that the enzyme becomes transgalactosylating. It now starts preferring to actually transfer a galactose to another galacto-oligosaccharide rather than hydrolyze. And this suddenly means that such a truncated beta-galactosidase from Bifidobacterium can actually be used in situ in a dairy product. So in a normal milk, in a normal yogurt, whatever. And that is, of course, offering a lot of new opportunities. So if we look at what does it take to make a sugar or calorie reduction claim in Europe, well, it means that you have to have 30% reduction in the energy value to make energy reduced, and the same for sugar. If you want to make a claim that this product is reduced in sugar, you have to have a reduction of at least 30% compared to a similar product. Then you can make a claim. And this then shows applying this enzyme. If you apply this enzyme in a plain yogurt, you will have to start with 4.6% lactose as a normal level of yogurt. You add the enzyme, and then of course you can only have a yield of 50% of the galacto-oligosaccharide, because when the enzyme is working, it releases a glucose. So 50% will always be released. So your maximum yield is 50%. But you see that applying the enzyme, we would then have 2.2% fiber form, and we will have 2.4% sugars left, meaning a sugar reduction of 47.8% in such a product. And at the same time, generating a fiber, which is really good for you. If you have sucrose, you can do the similar exercise, but of course, because we are not really touching the sucrose, you would only have a sugar reduction of 25% compared to the non-enzymatically added product. I think no matter what you do, if it doesn't taste good, you can't really sell it. So you can do really nice and healthy stuff, but it also has to taste good. So of course we have then done sensory analysis, and what you see is that there are no difference in sweetness compared between the enzymated and non-enzymated dairy product. And also we didn't have any off flavors. That's actually always a challenge with the enzymes, that especially dairy is a very sensitive product, so if you have a little bit of lipase or you have a little bit of protease in your enzyme product, you can easily get some off flavors. So this is a very pure enzyme. As a positive change, we do see that it's a little bit of stirring resistance and thickness on the spoon, of course because you have generated a fiber, so it actually has that small effect. And then my last example is going back to the cereal world. And in this case, this will be about how to achieve an oxidative effect in bread making. Oxidative enzymes are actually applied very widely in bread making. And the functionality is really that you get better dough handling properties. For instance, a dough that is less sticky, so it's easy to handle. Improved dough tolerance, improved bread quality, improved crumb structure, improved volume. It can also supplement or replace chemical oxidants, which I will show on the next slides. And then of course it can to some extent replace gluten, because you get this stronger gluten formed by the enzyme, and therefore you don't have to add so much gluten. This particular enzyme's mechanism is that it will use glucose or maltose, which is present in the dough, in the flour, and then it will oxidize to the corresponding lactone, and under consumption of oxygen produce a hydrogen peroxide. The hydrogen peroxide can then react on the free thiol groups that you have in gluten and form disulfide bonds, and by doing that you form a stronger gluten network. The advantage of this particular enzyme is that it can use not only glucose but also maltose, because maltose is actually very abundant throughout the dough process, while glucose is being used up by the yeast. Of course, the enzyme is also depending on oxygen, which is also being used up by the yeast. But there we do see that there is some diffusion of oxygen from the surface, and also when you are actually kneading the dough, you introduce new oxygen. So this is an advantage. And this is just trying to illustrate a little bit more graphically how do you imagine this. Here you see the gluten structure. You have the glutenine and the gliadines, the smaller parts. And then you have the free tyrol groups. And what then happens is that because the hydrogen peroxide which is formed is then oxidizing these free tyrol groups to disulfide bonds, and thereby linking the different subunits of the gluten stronger together, and you see a stronger gluten. And this is actually very clear if you do a confocal laser scanning microscopy of the dough. We sell this product as SureBake, so that is just the name for the enzyme. And you see here a control dough, and the yellow is actually the gluten stained for protein. And then you see over here where the enzyme has been added. And I think it is quite clear how in the dough where we have added the enzyme, you see a more coherent and more connected gluten. And that if you were touching this dough, you will feel it like, hey, this dough I can stretch more, it's much more elastic and easier to work with, a stronger gluten. And this then shows an example. This is what's called US no-time dough. And it shows the only difference between the two breads is one is baked with the hexose oxidase, the other is baked with bromate, and you get a similar comparable result. So to conclude, enzymes are really used in food processing as catalysts for a lot of things, and they are processing aids because they are inactivated in the final product. I showed here an example of how we could enhance the health and nutritional value of a product by creating a GOS fiber, for instance. Also producing soluble fiber content was the GOS fiber. It can also be increasing bioavailability, for instance, of compounds. Then in situ generation of ingredients, so you actually utilize like the lipids that are present naturally in the flour, and you generate in situ ingredients. It can be improving the texture and taste. And then of course it can very much be about reduced cost and increased yield, so you could say very much a sustainability thing. Also overcoming raw material variations. And a big application of enzymes in baking, for instance, is enzymes that modify the starch retrogradation, so the bread will actually stay soft and attractive for longer, which means you would throw away a lot less bread. And that, for instance, is an example for reducing food waste. We have also recently launched an enzyme which is being used for wheat processing, where you are milling flour, and where by adding the enzyme you actually has to use less energy in your rollers in the mill to generate the flour, things like that. So I hope I have convinced you a little bit that all the above, so this whole use of enzymes in food processing can help enable clean label solutions in different aspects of the word, simpler label, etc. So thank you for your attention.
Thank you very much, Charlotte. I would like to see check off 3 points from Lynn's presentation. Consumer benefits in these 3 examples that you mentioned here. Especially in the galacto-oligosaccharide, you have a health benefit of prebiotic in the product. The other one is, have you involved the consumers in this? That you have to ask your customers, I guess.
Yes, I mean, we certainly work a lot with our customers. So you could say most of the consumer contact is, of course, through our customers. But as I showed you the first, where there was really being asked clean label what are clean label decisive arguments, that is actually something DuPont has been part of doing. So we do go into that kind of consumer behavior things.
So you look into the consumer acceptance regarding enzymes in as a process.
I would say not particularly regarding enzymes, but probably more about, so what is it that people are looking for.
Yeah. And the third point is communication. Is this being communicated in any way, or is it that you can use a shorter label or a cleaner label as communication?
So what being communicated?
The use of this enzyme or process A.
Yeah, DuPont works through the different organizations like AMFEP in Europe. So I'm actually, since I'm really in R&D, I'm probably not the right one to ask the question, but I know for sure that we are working very actively in AMFEP and through these different organizations. Yeah.
So if we don't underestimate the consumers, they will accept this and they will look upon this as a good way of improving food quality and sensory qualities.
I hope so, but I totally agree with Lynn. I think this is. I think we as scientists tend to think if people just understand what it's about, they will like it. But I don't think that is how it is. I think it's very emotional. And I think you're trying to bring rational arguments on something emotional. And I think that's very difficult. So I think, personally, I think the best way to convince people is if the benefit is really very good. I think, for instance, for DMO enzymes, to me, the best example is we like to eat cheese. And if we don't use recombinant chymosin for producing cheese, we have to use calf stomachs. Is it really ethical? Is it really correct that we are killing young calves huge amounts to be able to eat cheese, when we do have a perfectly safe and good way of producing a recombinant identical calf chymosin and use that? To me, that's one of those where I think the benefit is pretty good, and I think a lot of people will see the reason to do it.
It seems like we in the north are more eager to accept the new technologies.
Yeah, but I think also in the US they are certainly also not really questioning GMO technology, actually.
Okay, thank you very much.